Larry and Sergey said to me, we've decided to drop out, and somebody wrote us a check. We're going to start a company. And, famous last words, I said, you're never going to make money. And Larry said, this is not about making money. It's about building the best search engine.
It's going to be hard for me to get you to commit and say when you expect, AGI to happen, I bet. If you can timestamp the knowledge available to a language model to 1904, would it predict the relativity paper of Einstein?
And I was asked, do you think that computers can play the game of Go?
Yeah.
And I remember saying, not in my lifetime. I was wrong. It's done, and now we take 200 million folded proteins for granted.
Hi, everyone. This is the Tech Surge Deep Tech Podcast presented by Celesta Capital. Each episode, we spotlight issues and voices at the intersection of emerging technologies, company building, and venture investment. I am Sriram Viswanathan, founding managing partner at Celesta Capital. If you enjoy Tech Surge, now is a perfect time to hit the like and subscribe button. And while you're at it, you can leave us a review on your favorite podcast platform. If you're just discovering us, visit techsurgepodcast.com to sign up for our newsletter and check out the archive of some very interesting past episodes.
At Celesta Capital, we invest in latest emerging technologies. So our team is constantly running analysis. Agents that help with that, but only when they can reach the context and tools where the data and work actually lives. With the recent launch of custom agents, Notion became the collaborative AI workspace where teams and agents work side by side. And now, their new developer platform is turning workspace into infrastructure developers can build on. New primitives are included in the developer platform that let teams sync any data source into Notion, build tools for Notion agents, and orchestrate any agent inside it. Using the external agent API, our team is able to bring our own in-house analyst agent seamlessly into Notion with its own triggers, tools, and permissions. We assign it research, it pulls, analyzes, and models multiple data sources, and we review and approve in our normal workflows. Learn more about Notion's developer platform today at notion.com/techsurge. That's all lowercase letters, notion.com/techsurge to try Notion's developer platform today. And when you use our link, you are supporting our show. Turning the world's messy, unstructured information into a clean answer is one of the hardest problems in computing. And our guest today has spent 40 years working on it. Dr. Prabhakar Raghavan is Google's chief technologist. For most of the last 14 years, he ran the products that more than 1 billion people use every day: Search, Maps, and Ads. And before that, Gmail, Drive, and Docs. His teams launched AI Overviews, Circle to Search, and Lens. But before Google, he founded Yahoo Labs and spent more than a decade as a researcher at IBM. As a theoretical computer scientist, Dr. Prabhakar has had a rare journey from the research lab to becoming one of the leading technology executives, influencing how billions of people find information. In this conversation, we trace that arc from the early days of web search to advanced algorithms behind today's artificial intelligence, and where he thinks we are heading next. So Prabhakar, I think what I thought we might find interesting to talk about, obviously there's, it's very target rich. There's so many topics we can get into. But what I'm really interested in is to start off talking about your original career as an academic, and then obviously you were at IBM, and you spent a lot of time in research areas, and that sort of led you to many commercial opportunities, including at Yahoo and at Google. And that's a long career arc. So can you just dwell on, what it takes to be a hardcore researcher, like the way you are, to become an operator, where you actually had commercial, sort of business objectives and all that. And that arc is a very interesting arc. Not very many people have the luxury of having been involved in it. So talk about that.
I think luxury is a good word for it. when I was a young scientist at IBM Research, I had a mentor who had this board in his office hanging, and it said, "Influence or perish." And back then, I was completely happy letting that translate into scientific influence. And so I did that for many years. But when I moved to IBM's Almaden Research Center in the Valley, I was struck by how many of my peers were doing these exciting things, building artifacts and products impacting billions of people. And it struck me that that was a form of influence that I'd never quite experienced before. So I was piqued by that. And I think the signature moment may have come in the mid-90s. One day I was driving home, and I hear this speech on the radio by Mark Andreessen. And up until then, like most of us, I was thinking of the web as a thing that you browse and discover pages and so on. But Andreessen made this amazing point that this would be the foundation for the next century's economy. And that had a really profound impact on me. And I said, okay, it's time for me to get beyond scientific influence and parlay that.
This was the Mosaic days.
This was soon after he was Mosaic.
Yeah.
But the point he made that this wasn't just about foraging around for information.
Right.
It was a transaction-based economy on the web. There was such a profound point that said, okay, I got to be a part of this.
So what did that, I mean, it just so happened that you were also doing a lot of research in relevant areas for what that inflection was about to occur in the industry, because you were focused on algorithms and maybe perhaps not search per se, but you were involved in optimization and randomized algorithms and all of that. So how did that, why did you choose that area as an area of interest for you?
Well, so you're right. I was working in optimization and algorithms and theory. And recent speech touched on something really interesting. If this is to be the foundation for a new economy, you need something that connects supply and demand. And the central piece of that is some form of search and discovery, right? And you may well remember what it was like back then to find information. We were all still learning our way around it. So it seemed to me that this search problem, however you define it, would be critical. So I went to my team the next day and said, we're going to start an effort in this. And
this was at Watson?
At Almaden.
Almaden, yeah.
And I had a great team. I'm fortunate, and a whole bunch of them signed up and said, yeah, let's do it.
This was even before it was defined as a search problem, correct?
Just about. To give you an idea of the vintage, there were early engines like InfoSeek.
Right. AltaVista.
Yes. AltaVista was just coming around the corner.
Right.
Yeah.
Right. And of course, the infamous relationship with Yahoo that Google made in those early days when Yahoo forgot that they were really in the information retrieval business, and they thought something else, right?
Well, I think all of these firms were jockeying in some way or form. There was no Google at that time, to be clear.
Right. But I want to stay on this point. So at IBM, which is really where you got pretty well known for your core theoretical work in fundamental sort of building blocks that are now pretty commonplace, I would assume. But when you picked those areas, did IBM have a very focused effort around software and algorithms? Because they had actually made that switch already. In fact, arguably, they had Watson before some of these other efforts were there for information retrieval. Was that not true?
I think at that point, the real forerunner was the Almaden Research Center grew out of IBM's storage systems division.
Right, SSDs, yeah.
SSD, and built relational databases.
Right.
And so a lot of the research there was around, okay, how do we make sense of information? And that was in the sort of gestalt around.
Right.
Of course, a lot of that focus was on enterprise relational data.
Right.
And the web was just a new frontier that was opening up. And that offered such a new canvas.
Right.
And so it didn't require any sort of official strategy. It was like a natural extension of what was already going on.
Yeah. So you would accept the point that IBM, even though had some very early sort of signals on what is coming down the pike in terms of technology evolution. Would you say that IBM was very prescient in doing that, and have they lost that?
I don't want to comment on what IBM has and does not have, but one of the nice things in an environment like IBM Research was you had the freedom to look across the industry and the technology,
right,
and dream about new areas, and that freedom is really empowering. So someone like me who was supposed to be doing algorithms in theory could wake up one day and say, let's get into web search. And that was a great thing to have.
Right. But the scale of the information that was online at that time was minuscule compared to what it is today.
Yes and no. So let's go through a little bit of an exercise.
Sure.
Right. If you look back 75 years, all of computing pretty much was in physics labs, and all of the information was structured, very structured, had rich semantics. Over the next 25 years, computing came out of there and into the enterprise, payroll, accounting, and so on. And the information still was largely structured. It was generated through transactions and so on. What changed in the following 25 years, up until the end of the 20th century, was the explosion in unstructured data, right? And so I wouldn't say it was minuscule at that time. In fact, what changed between 1975 and 2000 was the volume of unstructured information.
That exploded.
That just exploded.
Yeah.
And I think the amazing challenge ahead of us then was, okay, if most of the volume is unstructured and most of the value is structured, how do you reconcile these, right?
Yeah.
And that was the movie that followed.
I see. So, I used to work in my old days, I used to work for Andy Grove, and he had this famous line which said, let chaos reign, and then rein in the chaos.
Yeah.
So you as a, hardcore computer scientist, what would you have? Would you have this problem of structured data growing and scaling, or would you have this problem of, unstructured data just exploding and trying to put some structure around that unstructured data, which is a tougher problem to solve?
So first of all, you as a computer scientist don't get to choose this. What is happening was computing was going to the masses.
Right.
And the masses were largely producing unstructured data. And that was just a reality.
That's just the way it was.
So deal with it. I think we were all trying to devise these fancy entity extraction algorithms and machine learning algorithms to spot the salient and important concepts in documents. And the unlock turned out to be a beautiful market mechanism, not a technology. The unlock consisted of allowing the market to ascribe values to words and tokens and phrases.
Yeah.
And this became the economic underpinning of, $1 trillion economic underpinning of the web, right? And that market mechanism was something that I would say, as a computer scientist, you got a little surprised by. But a few of us were listening to these leading thinkers in microeconomics and auction theory and so on. And they were the teachers. If you paid attention to them, you realized that instead of writing a better machine, entity extraction algorithm, let the market decide. And structuring of unstructured data would happen. The pearls of structure would be extracted by the market. And that's what ended up happening. And this was an amazing revolution. And probably the first time computer science and economics met in a really meaningful and deep way.
Yeah. So we're going to get into AI and in the present day sort of, technical and business challenges and all of that. But just lingering on this phase of your career in the early days, can you see a straight line to where we are today in just projecting, knowing what you knew then, is this where we would have ended up?
Yes and no. You say straight line, and a straight line is a very rigid object, but I think I can see a piecewise linear function.
Piecewise linear function.
That would have gotten us from there. And there's a number of steps, and we can talk about that.
Sure.
But it doesn't hindsight is super powerful. You can say,
of
this
course.
epiphany and that, but really at every given point in the last 30, 40 years, we've been okay at trying to figure out what's happening in the next 3 to 5 years.
Yeah.
We've not been great at, extrapolating 30 years out.
Yeah. Okay, so let's move from the IBM period when you were actually looking at, you're influenced by, in Reason's speech, and there's this proliferation of unstructured data coming up, and that was profoundly significant. And then you went to, after a bunch of other places, you ended up in Yahoo, and at that time Yahoo was arguably the leading search destination, and then you moved to Google after that. So talk about what, there's a lot said about how Google really took search away from Yahoo at the right point in time. They were in the right place, all of that. There's enough history written about that. So I'm less interested in that. What I'm more interested in it is technically, what was appealing to you at that point in the mid-90s, where what Google was doing, because a lot of this ties back to link analysis and PageRank and all of that, which is some of the core research work that you were doing.
Yeah.
I'm trying to understand what attracted to you to that technical problem as Google defined it versus many others that were trying to solve the problem.
Well, I'd say, first of all, the technical problem was out in the air.
Yeah.
Right? It wasn't necessarily defined by one company or the other.
Yeah.
But if you rewind to then, I would say even the early engines
Yeah.
had a lot to contribute at that time. So I'll give you an example. Over at Inktomy, Eric Brewer and Paul Gauthier said we could put together these networks of workstations, what you would today call a very primitive multi-tenant cloud.
Mm-hmm.
So there you had a technology being manufactured that people hadn't really thought about, and that laid the foundation for a lot of what came later, whether at Yahoo or Google or whatever, right? Also, what were we preoccupied with at that time? The thing we were preoccupied with, given our text-based ranking algorithms, was that spammers were getting pretty good at figuring out how to deceive these algorithms. And so the designers of these engines were trying to figure out, well, how do you measure authority from a source? How do you measure trust in a source, right? And if you think about these, they become the motivating problems for link analysis that was to follow.
Right.
Right?
For the benefit of the audience, just give a beginner's version of what link analysis really means.
Sure. So the simplest form of link analysis, or at least the way we thought about it in the mid-90s, and again, this is almost before Google even existed.
Right.
Larry and Sergey were grad students at Stanford.
Right.
Was if a page has lots of people pointing to it, then it's probably a good sign. Now, that's not always a good sign because it's, are they finger pointing or just pointing, right? But these are signs of authority. And one of the things, the landmark that we all recognize, of course, is Larry and Sergey's paper it was a 1998 paper called The Anatomy of a Large-Scale Search Engine.
Right.
And it introduced PageRank, of course. By then, we already realized that simply counting the number of n-links wasn't good enough. So we had Larry and Sergey's PageRank innovation. We had, at my group at IBM, ideas developed from John Kleinberg on a different style of link analysis. And one of the things we look back on now is 30 years before we did all this work, in the mid-60s, there was a great deal of work on scholarly citation analysis that is a direct antecedent of all of these things, right? So the same kinds of algorithms were proposed in a different setting to measure which journal is important and which scientist is important.
Which publication from a scientist is more important.
Right.
Right.
And so those ideas sort of filtered down. And the thing we shouldn't underestimate is this all sounds like purely a technological play, but one consistent theme that we can talk about in this arc you're painting is users also change. You see, it's a false premise to say that users sat still and the technology kept evolving. It's actually a two-player game, essentially. And as the technology evolves, so do user expectations.
And user behavior, how they actually interact with the system.
Right. So whereas if formerly a user might have been content with trying to find the homepage of United Airlines or the price of a particular camera. Now they had more complex needs, like, well, this is my kid's daycare. What time do I need to leave work in time to get there in time? And these aren't, straight web page retrieval. So not what you would think of as classical information retrieval.
Right.
So users have evolved as well. And so as we brought in these new algorithms, the demands and expectations change. And that continues to today. As you evolve engines and information sources, users quickly adapt and say, oh, it can tell me that. Well, let me ask something more interesting.
Sure. But, this is the interesting point that I was trying to allude to earlier in terms of being able to draw this straight line between your fundamental work at that time, or at least, some of the things that Google was working on to where we are today in artificial intelligence. Because if I were a betting man and to have, 10 companies, and if I had the option to say which one of these companies is going to have a great shot at figuring out what the right thing to do and how to do it in inference, it wouldn't be surprising if most people ended up with, Google probably has a good shot at it. Not because of its business prowess and influence in the industry and all of that, but just the core technical problems that they were trying to solve at that time, which naturally sort of leads itself to, GPT and AI in the current form. Would you agree with that?
Well, again, the arc is, from the founding of Google in '98, to getting past the kinds of questions I was talking about, like, when do I need to leave work to pick up my kid in time?
Right.
There are a couple of other generations we went through before you get to LLMs.
Right.
One simple example I like to give is maybe almost 20 years ago, those of us in the search business recognized that what you're after is not the query, but the intent underlying the query. So when a user says, what's the height of the Eiffel Tower? You don't want to retrieve a lot of pages that talk about the height of the Eiffel Tower, even though they might contain the answer.
Right.
Wouldn't it be great if you just said 300 meters? In pursuit of that, you start to build these artifacts. For instance, you want to build some sort of knowledge graph of facts that says the height of the Eiffel Tower is 300 meters, the height of Don Knuth is 2 meters.
Yeah.
And, systems that can automatically try and say, wait a minute, something doesn't make sense. It says Don Knuth is 300 meters tall. It doesn't look right. And what this took was a lot of automation you may not think of as AI, but it did certainly take primitive LLMs already to try and make sense of a page and said, oh, lots of pages seem to converge on 300 being the answer to the question. So
just give that as the answer.
Right. That's the highly likely answer.
But that still arguably is a look back sort of a thing, because you're not really predicting what the user is going to go do with that. Is that the change with AI? Because, one might argue that the difference between a search sort of a platform versus a shopping platform is where the shopping platform presumably can take advantage of what you're searching for and predict what you're likely to buy and give you some relevant things to buy, versus search is sort of dropping you off when you've got the answer and not really fulfilling your next 2-3 steps of action. I mean, is that the way to think about it?
I think the distinction you're making is potentially a product rather than a technical distinction.
Sure.
Because, the reason I gave the example of the Eiffel Tower is in extracting that answer, 300 meters, by looking at lots of web pages, there's already a lot of language modeling going on that's trying to predict tokens within there.
Right.
And then you take 300 and escrow it somewhere in a knowledge graph as the definitive answer.
Right.
So that when a user comes and types that prefix,
you're able to take that.
Right. And so...
And in the process, you've actually assigned some weights to that.
Correct. Exactly right. So in doing this, you have the rudiments of what you're calling predictive. Also remember that we tend to narrowcast the notion of a language model to something that a transformer does. But in fact, there are other language models that have been around for 30, 40, 50 years.
Which are not based on transformer.
Exactly.
Which I want to get into that.
Yeah.
But before you go there, I want to just go back to the earlier point you made about Larry and Sergey's work on search. And this is obviously the time when you and Larry and Sergey's guide, Rajiv Motwani, who's a good friend of all of us. And
Yep.
He was a collaborator with you,
Yep.
and you wrote a book, and
Yeah.
the randomized algorithms. Can you talk about where that fit in the lead up to search, or was it a precursor? Was it?
No. So they were graduate students, they were very bright graduate students, and we would actually meet every now and then in Rajiv's office, and we'd say, well, here's what we've done at IBM, and they would say, here's what we've done at Stanford, and this is sort of a free flow technical interchange.
Right.
And there was a day early in '98, I think, when Larry and Sergey said to me, we've decided to drop out, and somebody wrote us a check, we're going to start a company, and famous last words, I said, you're never going to make money. And Larry said, this is not about making money, it's about building the best search engine there ever is. And they went on to do that. Kudos.
Information of the world in your fingertips or something like that, right? Or
Yeah.
indexing, whatever, right.
All of that, right? But the point was their primary goal seemed to be, what does it take to deliver a user experience that far surpasses what we have today?
Right.
And they succeeded.
All right, so now let's fast forward. So now you're at Google after a stint at Yahoo and all of that, and you originally had lots of responsibilities, and then you currently are the chief technologist. But in the first year, in 2012, you really took over Gmail as your core team, and Smart Reply and Smart Compose and all of that. There was clearly an expansion of Google's business from search to a whole bunch of applications, and Gmail was the first such application that they made available. So talk about that period and why Gmail, why mail was chosen as an application where Google could expand to.
I think there were, productivity is a natural extension of seeking information, because once you seek information, you want to act on it, and being able to communicate. So that led to the whole suite beyond Gmail, Docs, Drive, etc. To be precise, it wasn't my first year at Google. I joined, it was soon after. But it was an exciting time because on the one hand, you had these user experiences that were very classic, editing a document, writing an email, etc. But at the same time, it was clear that something new was in the air. And for me, one of the realizations was that, I found myself and my colleagues around me, a lot of the emails we wrote were incredibly predictable. There were things like, I concur, approved, yes, let's do Friday. And if you look at the context surrounding that user, it's almost the machine should know that that's what they would want to do. So, so go through, join me in this thought experiment.
Yeah.
Suppose instead of, you're sitting there with your Gmail in front of you, you have a QWERTY keyboard, but suppose those keys suddenly morphed into plausible, contextually correct responses. Okay, and that was the genesis of Smart Reply. I talked to some engineers and said, could we do this? And of course, remember, this was before transformers.
Right.
So we came up with this user interface where the thing would compute 3 responses based on a then popular language model called long short-term memory.
Yep.
And a few months later, we launched this, and somewhat to our pleasant surprise, we quickly got about 10% of all Gmail written by machines and selected by users.
So effective. So let's just pause there for a second. I mean, this is some early rudiments of this had the predictive aspect of predicting the next token, and you had it in word processing. I mean, you could actually start typing, and it'll actually guess what you're going to be typing next. And you're alluding to something similar in that context, right?
Right, and
LTSM was the basis on which that was built.
We built it in LSTMs.
LSTM, sorry.
Yeah. And exactly right. So this was starting to hazard guesses on what you were about to type, both in replies. We first did in replies because if you think about it, that's the place to start naturally because you can pre-compute offline.
Yeah.
Right. But then we got to the point, I think there was some IO where Sundar kicked off his speech with this. As you typed the Gmail, it would compose and finish sentences. Of course, today, these experiences seem, somewhat quaintly archaic.
Yeah.
But back then,
But those are the seeds.
Those
on
are the
which
seeds for-
the next token prediction.
Yes,
has
generative
come about.
AI.
Generative AI has happened.
yeah.
So before we talk about the algorithm evolution itself, the portfolio expanded. So obviously Gmail, and you could see patterns where contextual information and to some degree prediction using some sophisticated algorithms could result in providing the user with more relevant information and leverage the user's intent more. Is that correct?
That's totally fair. I'll give you another small example that we launched around the same time. We have Google Drive.
Yeah.
Right? Common scenario. You're walking into a meeting. There's a document you need for that meeting. Why doesn't it just pop up?
Yeah.
And so we said, let's reconfigure the Google Drive screen so that the document you're most likely to need is right at the top.
Right.
Okay? And that uses your context, like, what's your calendar saying, what are documents you touched recently,
Which location you're in.
etc.
Yeah.
And pops it up, right? And so the point again was to enhance the user's productivity and experience by giving them contextually relevant information right there. Now, this is not a matter of completing words, but ultimately it comes from the same, place.
Right. What strikes me is, as you said, there are looking back, it's always easy to sort of be amazed at how obvious and quaint some of these things are, but not everybody got it because arguably at that time Microsoft had this incredible wealth of user context and content available to them because most of the productivity apps were within the umbrella of that platform, and lots of reasons why they ended up where they ended up. But what I'm struck by is that the technical talent within Google seems to have at least known what's coming down the pike as to what the user may really care about. What drove that? I mean, how did you know what, context and content go hand in hand for the user? Because you didn't have as much of, other than the search information, you didn't have as much of the enterprise software behavior as much as some other platforms did, like Microsoft and others. But you figured that out. You guys figured that out. What led to that?
I think there's a couple of things I would say. The first is the founders, as is famously published and written about, were always very focused, maniacally focused almost, on users and their needs. And
were they focused on the users or were they focused on the information?
Well, information was the mission. Okay, but users were sort of the motivation.
Well, the users were sort of a necessary byproduct of what it feels like as an external user. Because when I'm actually outside, Google cares less about me. I'm just making a very subjective sort of a comment because as a user, I think Google cares more about all the places I touch, all the information that I have access to. And with that, they can serve me more. They serve me less by knowing more about me. Is that a fair statement?
I think that's sometimes overinterpreted.
Yeah.
You'd be surprised both at the design principles and the practical realities of how little it takes to do a great job of servicing your information needs, right? So in the example I gave you of Google Drive just now, it's not like we had to look at all your touch points. It's essentially your calendar is a strong signal and a couple of other things, the most recently touched documents, and that's about it. And we can do an excellent job of predicting. So we sometimes get, there's this principle of Occam's razor, which, right, go for the easiest thing you can get away with.
Yep.
And usually it's far simpler, even though in theoretical consideration, you have all of this to deal with, right? The other thing I'll point out is Google is a cloud-native company.
Yeah.
We grew up with the cloud. So we don't think of information as sitting here or sitting there or whatever. Our developers think of, APIs and access to information in the cloud. And that changes your viewpoint. And, building on something, when we were looking at grammar correction in Google Docs. I remember this conversation I had probably 10 years ago with Jeff Dean, and he said something like, well, somewhere in the cloud, there's a record of every correction that everybody has made. Surely you can learn grammar from that. So think about it. We don't think of grammar as a subject that has been formally studied.
Or as a rigid structure.
Yeah, exactly.
You can learn it from just looking at
Right.
and
that mentality pervades a lot of what we do.
Yeah. And the fact that you have now this suite of applications, there's a lot of cross-application learning that you can extend to...
Again, less than you would imagine.
At Celesta Capital, we invest in latest emerging technologies. So our team is constantly running analysis. Agents that help with that, but only when they can reach the context and tools where the data and work actually lives. With the recent launch of custom agents, Notion became the collaborative AI workspace where teams and agents work side by side. And now, their new developer platform is turning Workspace into infrastructure developers can build on. New primitives are included in the developer platform that let teams sync any data source into Notion, build tools for Notion agents, and orchestrate any agent inside it. Using the external agent API, our team is able to bring our own in-house analyst agent seamlessly into Notion with its own triggers, tools, and permissions. We assign it research, it pulls, analyzes, and models multiple data sources, and we review and approve in our normal workflows. Learn more about Notion's developer platform today at notion.com/techsurge. That's all lowercase letters, notion.com/techsurge to try Notion's developer platform today. And when you use our link, you are supporting our show. In 2017, 8 researchers at Google published a paper titled "Attention is All You Need." It was about machine translation. It said nothing about chatbots or artificial intelligence as we talk about it now. That paper introduced the concept of a transformer, the architecture underneath almost every modern AI system. By this year, it had been cited more than 250,000 times, which puts it among the 10 most cited scientific papers of the century. Prabhakar was inside Google as that idea went from translation trick to the foundation of everything. Here's how he tells it.
So it's not the case that, we're going to look at your Gmail and use that to condition your ads or anything. We don't need to do any of that.
You don't need to do that.
Yeah,
right.
It's it's much simpler than that.
Right. And we're going to talk about Gemini. So now let's talk about this long arc from PageRank to Transformer, right? So, of course, in parallel, there's a completely different podcast that one can have about the other sort of innovations that are happening in deep learning and Hinton's work and Fefili and all of that. That's almost on a separate track.
Yeah.
But if you were to sort of say, okay, so now you got the search sort of figured out, you've got this platform, you've got all this information, and it becomes obvious for the industry to recognize that the users are actually going to want to have some degree of prediction in whatever activity that they're engaged in, whether it's, I'm picking up my child, the system is going to tell me how the traffic is ahead of time, or I'm going to go to the East Coast,
sure,
tell me about the weather and all that. So there's a degree of expectation related to prediction that is already coming into the play in the consumer expectation.
Yeah.
Now, there were different algorithmic work that happened in parallel, right? So obviously, as you point out, much before Transformer, there were other initiatives. Can you walk us through what are some of the major inflection in algorithmic work that led us to where we are now? I mean, of course, there's CNNs and there's.
I think those are all pieces of it, right?
Yeah.
If I look back to, let's start with even image recognition, computer vision, and so on, right? So 20 years ago, the way we did that was to take a scene, then develop algorithms and deploy algorithms that analyze a scene and talk about, well, this is a cat, this is a chair, and these are bespoke algorithms talking about occlusion and what's in the forefront, what is in the background, etc. And we had, a lot of research going into how to devise those algorithms. And roughly 15 years ago, there's a bunch of people who said, you know what, let's just take deep nets and throw a lot of data on them and let it figure out what's a cat and what's a chair, right? And obviously, machine learning kernels have improved a lot since then, with that the performance. But the idea of a deep net, together with lots of training data, autonomously coming up with powerful predictive capability, but most importantly, not bespoke in any way, where it's trying to say this is in the front of that and occluding that and so on. This was one big step, right? And that's, you mentioned ImageNet and others. And I remember, I forget who it was, but one of the pioneers at that time, I remember, mentioned something like, this changes everything.
Yeah.
And back then, I think most of us didn't see exactly what it changed, but it changed everything, right? So that was the one big step, right? The next step, which...
But just to put a point on that, I think you're referring to the period when Fei-Fei Li was working on the whole AlexNet stuff, where she was trying to create a image database and all of that.
For instance, but even people like Joshua Bengio and others were very involved in this, right? But then the next sort of moment may have come when we switched into analyzing sequences, okay, and going from sequences to sequences. And certainly at Google, one of the primary motivations was machine translation, which was already a big thing. We had Google Translate already being used like 1 billion people.
Yeah.
And there was a dream of doing a much better job of this than we were doing. Right? And so that requires you to map sequences to sequences.
This was sort of the time when the attention is all that mattered paper, right?
About to happen.
Just about to happen,
yeah.
Right? But before you talk about that, where did CNNs fit in, and what happened to that? Why did that get prominence, and did that lose prominence subsequent to Transformer?
In a sense, yes, because the attention mechanism added something to sequence manipulation that was inherently powerful. You see, at the risk of oversimplifying a little bit, a traditional deep net, you pipe in a sequence and it processes one atom at a time,
right,
and pumps something out. What the attention mechanism does
looks at it as a chunk.
Yeah, it confers on each token some amount of influence from surrounding tokens and does this throughout. And of course, as you know today, the transformers we have confer the attention pretty long range, so-called long context models, right? And in the process, the quality of semantics improves to the point where it becomes almost anthropomorphic, and which is why LLMs have become anthropomorphized. We tend to talk about them as thinking and reasoning and so on, even though they are predicting tokens. And so that was a big unlock.
But that need to have a very long string context was memory constrained, correct? Or is it compute constrained?
It was actually, prior to the attention paper, even the notion that it really helps to look at surrounding words. So we used to have this saying at Google, you shall judge a word by the company it keeps. Right? And that was just becoming a thing with BERT and those early language models. And what the attention mechanism managed to do was take the next measurable change in outcome, where the predictions got so good that this thing looked conversant. And that was the transformer revolution.
So what was the aha in the attention paper? And describe the attention paper.
I mean, the attention paper formalizes the notion of minimizing a loss function, etc., as always.
Yeah.
But by carefully training the weights, the attention weights. Right.
On the adjacent tokens.
Not just the adjacent. You could go in theory.
As deep as you can.
Yeah. As deep as you can afford to.
As deep as you can afford to go.
Right.
Yeah.
Right.
And then you assign weights to those.
That's right. So part of the training process. So what does training consist of? First, you take every word in your lexicon.
Yeah.
And make it a point in some very high dimensional space.
Yeah.
Okay. And now you're getting a sequence of these points.
Yeah.
high dimensional space, right? And they are quote unquote attending to each other. That's the vernacular. Right?
Yeah.
Now, all the weights in the network and all the weights on these attention links are being trained through lots and lots of training examples to become really good at prediction by this thing called stochastic gradient descent,
Yeah.
right? And that's the standard method by which
Yeah.
right, you optimize. And the one of the interesting outcomes of this is it did also have a profound impact on computing architecture. And I know that's something, you come from Intel, and there, back when we looked at Intel CPUs, we would look at this instruction set that could do all these amazing things, and it could, add and move things around registers and all of that good stuff. But it turned out that the most central operation to these deep nets was matrix multiplication, right? So it became a very simple instruction set in some sense, but it had to be really, really, really good at matrix multiplication.
Yeah.
And then it turned out that the processors that did this exact thing were already available in gaming and graphics.
I guess what I'm really getting to is that in some point in this evolution, this attention paper was an important paper which required context to be held for as deep as you can go on the graph and assign weights and all of that. And the more you did that, the better the predictive accuracy was going to be. And at some point, this became a computational problem.
Yeah.
Can you talk about that? What was that inflection where people started recognizing, okay, this is, I'm going to be compute constrained.
Yes.
What was that point?
I think it was fairly early on. People working on transformers, whether at Google or other places, realized that if you just threw raw cycles at it, you would only get this far.
Right.
So people came up with lots and lots of interesting tricks. And in fact, it's interesting you mentioned branch prediction. One of the things that actually happens here is token branch prediction.
Yeah.
And that's one way of speeding things up, right? You can also mess around with the accuracy with which you do some of these multiplications to speed things up. And these are all tricks that people deployed fairly quickly in the early days of transformers.
Yeah.
And then you could still see that the slope of performance improvement lay well ahead.
Right.
So that's when the appetite became essentially insatiable.
So throw more compute at it so that you can actually train it more.
Yes, and by doing so, get better, predictive performance.
Yeah. So where are we on that curve?
It's
hard to say.
Hard to say. I'm not going to take a stab at it. One thing to realize is it's not just about it's not a single dimension of the probability of prediction accuracy being high.
Yeah. Because
now, by the time you impute semantics to what is coming out, it's really the outcomes users are getting that you care about. And that's less about predicting a single token accurately.
Right.
Right. And this is why people get into chain of thought and thinking models and so on and so forth.
Yeah.
Models that self-critique themselves.
Yeah.
And in an interesting way, we're at a point where on the one hand, you can floor the pedal and keep improving peak performance.
Yeah.
But there's always this notion of, okay, in the worst case, what are these models doing that we don't fully understand? You see the difference here with a conventional model of computing, like a Turing machine. You can have rigid assertions about what the machine will and will not do.
Right.
I give you two numbers, you will add it correctly. I ask you to propagate a variable, you will. I ask you to run a loop 50 times, you will. That sort of firmness of computing model is now lost. And instead, you have an incredibly high-level programming abstraction, which is natural language, the highest it can get.
Right.
But there's always this notion, okay, is it going to do exactly what I said?
Because that's where the context becomes important.
Yes.
So in this context, what is the next stop in the evolution of algorithmic development post-transformer? Where does diffusion fit in that? I mean, if one were to make this thing about LTSM to CNNs to transformer, is diffusion the logical next thing or no?
I would say the way I look at it is the industry and academia are looking at a number of successors to the
To
transformer
transformer,
architecture. Diffusion is one of them,
Yeah.
right? There is no clear front runner at this point, and there are certainly people who believe that there's plenty more mileage to be gotten out of transformers.
But explain diffusion before we talk about whether it's real or not. Yeah.
What do you mean it's real? It's
I mean,
very
well, when I mean that, whether it's the logical next step in
Yeah.
as being as profound as transformer, what is diffusion?
I mean, diffusion is a class of models
Yeah.
that's fundamentally different from transformers in that it is not just about predicting one token at a time. Think, if you will, and this is a crude analogy, of outputting the whole paragraph and then going back and fixing things up along the way, right? And you do that based on, a fairly detailed stochastic process underlying a model, but also a completely different way of training. So,
Right.
so in that sense, it is so different from transformers.
Yeah.
But ultimately, it's going to be judged by, does it get to better outcomes?
Right. And at what cost? At what
Surely,
computational
right.
cost and what,
I mean, yes and no. The thing history has always taught us is, with any new system, and I'm not even talking necessarily of language models,
Right.
you always begin with a cost that on day one looks large.
Right.
And the industry and academia are very good at riding that curve down and saying, what used to take us X, now we can do for 1/100th of X.
Right.
Right. And that's a natural progress. And, personally, as a person trained in algorithms, it pleases me to be in that situation
Right.
of something that performs well but has exorbitant costs, because now I have traditional tools to hack it down.
To hack it down.
Right.
There is an interesting thread developing today around research in diffusion worth noting. Stanford's professor A. Paul Raj is well known for inventing and commercializing MIMO wireless technology, which underlies all of today's mobile and Wi-Fi networks. We happen to know Professor Paul Raj quite well at our investment firm because he is a dear friend and advisor. What is less known in the professor's work is that his PhD thesis, completed in the early 1970s, may turn out to have a second life in artificial intelligence in relation to modern diffusion models. The thesis developed a mathematical framework for estimating, from noisy observations, how physical systems evolve unpredictably over time, including ocean currents, atmospheric circulation, and structural dynamics of buildings impacted by gusty wind. He used stochastic differential equations with a forward and backward operator structure to solve the estimation problem rigorously. Researchers in the AI community have recently noticed that this operator structure appears mathematically related to the foundation of modern diffusion-based generative AI, particularly when applied to simulation of the kinds of physical systems the thesis studied. Whether this connection yields something practically useful in generative AI is still being established, but it signals something we believe and continue to see more broadly, that the most important technology breakthroughs are often grounded in fundamental mathematics that was far ahead of its time.
A lot of what AI today is modeled after is how human beings learn, and how human beings infer things.
Yeah.
But there seems to be a very striking difference between the modern day AI systems and how a 3-year-old infers, there's a danger, or, I have to be safe, or whatever, because it feels like the training and inference are in situ. There's no bright line between I'm in a pre-training mode, and the child doesn't say, okay, the next 3 years, I'm not going to infer anything. I'm only going to, get myself trained. That doesn't happen. Human beings don't behave like that. Yeah. Do you see a difference between how modern AI systems are built versus how human beings fundamentally train and infer things?
I'd say yes, but the differences are somewhat more subtle, right? So let me bring to bear a few different relevant pieces of work, right? So first, here's an experiment that some friends of mine did, and they published it. So they trained Transformer on, I think, 12 million taxi rides in Manhattan. Okay. Then they would ask the Transformer to find, the path from A to B. And they did a pretty good job. Then they said, based on what you figured out, learned, draw a map of Manhattan. And it looks nothing like the real thing. So you see, the point here is AI's model of the world and our models, in this case, the real world model of Manhattan, can differ significantly. And
Even though it may actually give you
even
the
though
right answer.
predictively,
It can give you the right answer.
yes, right? And this is actually a very interesting finding. And, one of the authors of that work, and I have now started to build on it, we're doing more experiments where we're learning things about what happens when an LLM tries to walk down the street, literally. What does it see on the left, right, and so on? And sometimes it pieces together things it knows, but emits them in incongruous ways. So, for instance, you can get an LLM to describe what it's like to drive from San Jose to Santa Cruz. And depending on the run, because these things are stochastic, you might well have it say, as you drive down Highway 17 and merge into Highway 1, you see the gleaming Pacific on the right. Now, if you recall that route, you actually don't see the gleaming Pacific, but it is on your right.
Yeah.
Right? It's just not visible from where you are. Right? So this is a case where the world model deviates from the language model. Right?
How much of that is based on our lack of understanding on how we human beings process versus, is there some degree of...
Okay, but in this case, you know that your inability to see the Pacific from Highway 17 is not your inability.
Yeah.
It's the real world.
It's the real world.
And yet the AI managed to see it because it knows it's out there somewhere.
Right.
And
right.
it says things about the gleaming Pacific.
Yeah.
We also found, incongruities that would change what you would see, what the model described as seeing as it walked around Manhattan.
Right.
Depending on whether it was a day or night.
Right.
Okay. And so my point here is AI's model of the world, you're right, differs from our model.
Right.
And we've just started scratching the surface of this. Now, to your point of, is it true that a child doesn't hold aside a training period and then get, right? There are actually models now, this notion of test time.
Compute. Yeah.
Right?
Yeah.
Where as you're going along in inference, you're checking yourself and refining yourself. And that's become a good way of improving accuracy.
Right. I mean, it reduces hallucinations and all of that.
And so this is arguably a case where the model is trying to do what the child is doing.
Right.
Right? Or at a high level.
Yeah, without any undue consequences of making mistakes.
Right. Yeah.
So I guess where I was really going towards was that for the longest time, post-transformer, it became, it's become obvious that amount of data you have for training and, and the ability to hold, longer attention, it improves efficiency, and, accuracy and all of that. And that has led to compute as a problem.
Yes.
And then you alluded to this whole pre-train versus decode thing, which actually allows for, using memory more carefully. So for a foreseeable future, do you see that we are going to be in a compute constrained space, or do you see a change in that curve?
So if your intent is to say, do I see a magical architecture that shows up and fixes this? I'm not seeing it.
Okay.
Right. Of course, this shouldn't stop us from trying. We should keep trying. And we have colleagues and surely many other entities who are trying to get through this. There isn't a readily apparent bypass.
Obvious answer. Yeah. So I have to ask you a couple more things on the AI thing.
Okay.
It's going to be hard for me to get you to commit and say when you expect, AGI to happen, I bet, because, none of you want to comment on that. And I respect that. And because either you don't know it or you don't want to comment, which is perfectly fine.
Good.
But the question that I have is RSI. So when do you think our systems can actually recursively self-improve, and how far is that?
Look, there is some amount of that already going on.
Right.
Okay, we talked about test time compute, which is sort of a small version of that.
Right.
Right. One of my current interests that I'm spending a fair bit of time on is trying to use LLMs to prove theorems.
Yeah.
And it's not an entirely academic pursuit, because part of what we're trying to do is build these things to understand the deductive process in general. Right. And it's not easy. It also touches on one of your earlier questions about how the child learns. You see, if I want to use a language model to prove a theorem, it has at its disposal all of the history of mathematics. It has every success known to mathematics. What it doesn't have is all the failures known to mathematicians, but not to mathematics. You see, because nobody's writing papers about their failures. They stick in people's head. Mm. So in some sense, I think a key element of what's ahead for us is to try and figure out how to better endow models with what doesn't have a good shot at working, because that makes it far more efficient at self-improvement. Right? And that's one of the things we're learning. And so as we are trying to build systems to prove theorems, we find that a bottleneck is not having access to failures. And so you want proxies for those failures. And you're starting to see some appear in the different companies, but I think that'll be a key piece of it. And until we get good at that, it's a little premature.
The one thing that I was struck by when I was listening to one of the talks that Demis gave was that, if you can timestamp the knowledge available to a language model to 1904, would it predict the relativity paper of Einstein?
Good. And I've heard variants of this.
Yeah.
I had Professor Bruce Burnt, who's in the math department at Illinois. He is kind of the world's definitive expert on Ramanujan. And he said, can you rewind a model to the end of the 19th century?
And predict the Ramanujan theorem.
And all of them.
Yeah.
And the challenge he issued was that after Ramanujan's death, people have confirmed those using late 20th century mathematics, which is completely unavailable to this man. So how the heck did he do it?
Right.
Right. And so this is not just a single prediction. It's connecting across wildly different branches of mathematics.
Right.
And we're starting to see smidgens of that in the model, but not enough to say, yep, you could predict all of Ramanujan's identities or relativity or whatever.
So on the product side, in your current role, obviously things have moved from a simple text box search query to, Gemini and all of its flavors and Waymo and all of that. It feels like Google is not only a true cloud native company, it is really a cloud AI native company. Everything that you're doing is AI, infused. Is that the right way to think about it?
I think AI infused is the right way to think about it. But ultimately, I hope this doesn't sound repetitive, but it has to be in service of problems that real users have, right? So the fact that you have Waymos and these cars can now drive competitively, which is an activity that give or take 1 billion people on the planet can do. Okay, that's a landmark.
Yeah.
Okay. The fact that you can write competent code is an activity that tens of thousands of people on the planet do. Right. So all of these are moving along on a landscape of human capability. We're still far from being able to prove Fermat's last theorem. So there are maybe 5 or 10 people on the planet who could do that. So we're not up to matching that. And this is why when you ask about AGI and RSI, I don't think there is a simple straight answer, because you have the spectrum.
Yeah.
And we're sort of plodding along the spectrum. But I hope it's not AI infused in your mind for the sake of being AI infused. It's for the purpose of delivering user value.
Sure. And in the fact that you mentioned Waymo is great, because Google was obviously one of the pioneers in sort of being a bet on ADAS much before a lot of other people were doing it. You did it in a very expensive way, and it's proven to be a phenomenal thing for you. But we don't hear enough about physical AI or robotics as much. Is that not high up in the priority, or we just don't hear about it?
I think you don't hear much about it. It's also early in terms of where is the definitive value coming from? You see, robotics spans a very wide range, from autonomous robots wandering around Mars and doing things to assembly line robots that are in a very controlled environment. Right? And in some sense, we as an industry are trying to figure out what are the pressure points where AI could add the most value. Right? Obviously, there is a lot of AI has been ever since the original Mars rover, set off and did its thing, because the signal round trips to Mars are large enough that it's not a real-time control thing. It has to have a lot of autonomy, right? And so to that end, we already have AI deployed in certain eclectic robotics. It's not mainstream to the point where it's washing your dishes.
Right. So as we're coming to the close of this, can you talk about, you are in this incredible position of seeing cutting edge of everything that's going on, not just in the corporate world, but also, academics and all of that. Are there things that you see now in your vantage point that you go, wow, I never thought that could actually be feasible?
I think, it's very easy for me to rewind. And, I was, when I finished my PhD, I remember on an interview at one of the campuses, I was interviewing for an assistant professorship, and I was asked, do you think that computers can play the game of Go?
Yeah.
And I remember saying, not in my lifetime. I was wrong, right? So absolutely, another version of that, which nobody ever asked me, but I had in my head always, was in my lifetime, computers are not going to be able to do protein folding.
That was wrong.
That was wrong too, right? Yeah. So what?
Coincidentally from the same guy that did both.
Exactly, right? Yeah. And it's incredible because the idea there clearly surpasses what humans could do in a wet lab. It takes 5 or 6 years to fold a protein in a wet lab, right? So you went from sort of in vitro to in whatever you want to call the cloud, right? In silico. And the same trick somehow sufficed for Go as well.
Yeah.
And there are a few simple principles that took us from people like myself saying, okay, that's science fiction, not happening in my lifetime. So it's done, and now we take 200 million folded proteins for granted, and the life sciences community is using that to develop new.
And the rest is history, as they say.
Yeah, will be history.
Yeah, but give me at least one such long arc thing that you're skeptical that our current generation AI systems.
You want me to be wrong again?
That's the point, right? You're already setting a trend. You're wrong twice.
Many more than twice. Yeah.
But I'm more interested in figuring out what is it that you think is computationally or system-wide, it's a big enough problem that it is unclear whether in this decade it gets solved.
Oh, that's a much more contained question.
Exactly.
So I am willing to stick my neck out for that, even though this may still be proved wrong.
Yeah.
Right. I don't think these machines will, within a decade, prove the Riemann hypothesis.
Prove the Riemann hypothesis.
Yeah. And this is a famous 1850s conjecture by Bernhard Riemann on number theory, which builds on work of Gauss. And Hilbert, in his famous 1900 ICM lecture, called this out as one of the biggest problems.
Yeah.
And I think I'd like to say that reasonable mathematicians would agree with me on this, but I'm entirely prepared to be proven wrong again.
Well, by extension, I'm going to do some deductive reasoning and say that since you did not name AGI as something that is impossible, I'm going to assume that you're going to say within the next 5 to 10 years, that's going to happen.
I think, there I'm a little more careful with the definition of AGI, because the first thing I ask when you say as good as a human, well, at what task and which human, right? You're not, so clearly, let's say there's an Andrew Wiles-like person who's going to prove the Riemann hypothesis, right? At that task and matching that human, I'm saying it's unlikely in 10 years, right? So that's why I'm skinning this a little carefully.
So Prabhakar, as we try to close here, as you know, Celesta, we're obviously investing in very early stage, starry-eyed entrepreneurs that are, thinking of solving world hunger to everything that that they can touch their get their hands on. What advice would you give them as a hardcore technologist that has this vantage position of your learnings from the industry of 30 to 40 years and been wrong many times, but yet been incredibly successful?
Okay, that's a well-phrased question. Let me say one thing I've done, and I think many people do, is when they start off in their careers, they anchor heavily on what they've been trained to do and not enough on everything else they could be perfectly good doing, right? And in the sort of PhD community, this is sort of captured as students who can never give up their thesis and just continue working on the same thesis for the rest of their life. And like fashion, if you take anybody's career, all these entrepreneurs you're talking about, call it 50 years ahead of them, during that time, it's almost certain that there are 3 to 5 sea changes in the technological market environment. Each of these is going to require them to adapt themselves completely, and in the process, cast aside and abandon things they're holding on to from the past, right? So that ability to cast aside and glom onto something new, driven by curiosity, I think is going to be critical. And for me, I've changed careers a few times. I'm spending a lot more time now again as a scientist, and I'm very comfortable doing that. And it takes a certain curiosity, of course, but it also takes an amount of courage to say, that thing I was really good at, I'm going to toss it out and try my hand at something else. And your best and most successful entrepreneurs will do that, will cross that chasm repeatedly. And so I would say, if your young entrepreneurs were willing to embrace that, willing to embrace change, not fear it, they're in great shape.
Yeah. Both of us have young adults as children.
Yes.
And if you were to give them a word of advice in this time, what skill to sharpen?
You're presuming that my young adult children will listen to me. I would never dare to give them.
I can assure you, my young adult is not going to listen to me, but it's just a vicarious desire, to hope that they might listen.
I think they have to figure this out, but I think embracing change is the best thing you can do here.
But I guess a more particular question is that, it feels like applied technology, applied sciences was definitely losing its charm as we were growing up, but it almost is like reversal to the mean. So now more fundamental technology or fundamental sciences that you get back into there probably has higher shelf life. I mean, would you agree with that? And math and physics and
so I think these things will change very fast. The reality is that next big applied technology is not happening without the underlying science. The problem with basic science, I shouldn't say it's a problem, it's a feature of basic science, is some of these bets will pay off. You just don't know which one.
Right.
And so, you as a VC are used to sizing up bets, but really fundamental science, you invest in it because there's going to be payoff. And it's a mistake to start by asking, okay, which scientist is going to pay off?
Yeah. Well, Prabhakar, this has been just an amazing conversation. I can talk to you for a long time just for the heck of understanding Fermat's theorem and all of these various mathematical things that you live and breathe every day, and you speak of it with such aplomb, and I'm envious of your job, and congratulations on all your great success and continued work on fundamental things that shape our lives.
Thank you. Thanks for having me here. I've really enjoyed this.
A few things to take away from this conversation. The first is that the biggest breakthrough in history of search wasn't a smarter algorithm. It was an economic idea, letting a market decide what words are worth. The breakthrough often is not the technology you expect. The second is Prabhakar's career arc. Information started out structured and scarce, locked away in the physics labs. Then it exploded into messy, unstructured web. And now, for the first time, machines aren't just organizing that information, they're starting to generate new knowledge or cognition from it. Consider that one AI system out of Google has already mapped the structure of 200 million proteins, work that won a Nobel Prize for Demis Hassabis
and would have taken biologists generations. So the big question for the next decade isn't where these systems can index and sort through or even predict answers to questions amongst information already known. It is what they can discover that we have yet to even dream of.
Thank you for tuning in to the Tech Surge podcast from Celesta Capital. If you enjoyed this episode, feel free to share it, subscribe, or leave us a review on your favorite podcast platform. We'll be back every 2 weeks with more insights and discussions of all things deep tech. Bye for now.